Large language models are incredibly powerful, but they don't come pre-aligned with human values. To make them truly useful, we need to steer their behavior, teach them to be helpful, truthful, and safe. One of the most effective ways to do this is through reinforcement learning from human feedback, or RLHF. In standard RLHF, we first train a reward model on human preferences, pairwise comparisons like which response is better. Then we use that reward model to guide the policy, the language model itself, through reinforcement learning. The dominant method for this has long been proximal policy optimization, or PPO. But PPO has a critical flaw in real-world settings. It relies heavily on the absolute magnitude of reward scores. Now here's the catch. In many tasks, like summarization, chat completion, or instruction following, the rewards are non-verifiable. There's no ground truth. The reward model isn't measuring correctness like in math problems. It's judging quality based on subjective preferences. And here's what we know from decades of preference modeling. Reward models are much better at telling us which response is better than how much better. Yet most policy optimization methods, including GRPO, a popular variant of PPO, still treat reward magnitudes as meaningful. They standardize them using z-scores, assuming that a reward of 3 is twice as good as 1.5. But in non-verifiable domains, those absolute values are noisy, poorly calibrated, and often arbitrary. A score of 3 might just reflect a model's overconfidence, not actual quality. This mismatch, ordinal supervision paired with cardinal optimization, leads to unstable training, poor convergence, and suboptimal policies. So what if we could ignore the numbers entirely and only use the order of the rewards? That's the core idea behind Group Ordinal Policy Optimization, or GOPO, a new method that rethinks how we use reward signals in language model alignment. GOPO is built on a simple but powerful insight. If the reward model is trained to rank responses, then the policy update should only care about ranking, not magnitude. Let's walk through how it works. Imagine you have a prompt, and you generate 5 different responses. Each gets a reward, say -1, 0.1, 0, -0.1, and 3. In GRPO, you decompute the z-score of these rewards, centering them around the mean and scaling by the standard deviation. The relative differences are preserved, but the scale still matters. A reward of 3 gets a high z-score, even if it's just slightly better than the others. In GOPO, we do something radically different. We discard the raw scores entirely. Instead, we assign ranks. The best response gets a rank of 1, the worst gets a rank of 5. Then we map those ranks to a fixed, evenly spaced advantage scale, from -2 to +2. So the highest ranked response gets +2, the lowest gets -2, and the rest are spaced evenly in between. This transformation is entirely ordinal. It preserves the relative order of the responses, but throws out all information about how far apart they are in value. The difference between a score of 0.1 and 0. Irrelevant. The difference between a 3 and a 1. Also irrelevant. Only the ranking matters. Why does this matter? Because the reward model is trained to learn relative preferences, not absolute scores. It's a Bradley-Terry model at heart, optimized to predict which of 2 responses a human would prefer. So why should the policy update trust the scale? By using only rank-based advantages, GOPO avoids amplifying noise from miscalibrated rewards. It's robust to outliers. It doesn't get misled by a single overconfident or poorly scored response. And crucially, it's more sample efficient. Empirically, GOPO outperforms GRPO across a wide range of tasks. Summarization, chat completion, instruction following, on models from 1.7b to 8b parameters. Across all metrics, training reward, validation reward, LLMs judge win rates and benchmark scores, GOPO consistently wins. But the real story is in the dynamics. GOPO updates have higher gradient norms, especially when the number of completions per prompt is small. That means the policy learns faster. It consumes the KL budget, our safety constraint against drift, more quickly. And because of that, it reaches a high-quality policy in half the training steps compared to GRPO. Let's break down what this means in practice. In one experiment, we trained a QN3-8B model on TLDR summarization. GRPO took 200 steps to reach its peak validation reward. GOPO hit that same level of performance at step 100, and even better, it maintained a higher win rate against GRPO throughout training. At step 100, GOPO's policy was already beating GRPO's final model in human-like evaluations. Same trend on UltraChat. GOPO achieves GRPO's best validation reward at step 125, and the win rate against GRPO's final model is 0.53, a clear advantage. And on IFEval, a partially verifiable benchmark with strict formatting rules, GOPO not only converges faster but also achieves higher scores across multiple sampling temperatures. Its best performance lands in the upper right quadrant of the convergence plot, meaning faster, better results. Why does this happen? Mathematically, the variance of the gradient update in GOPO is driven by the sum of squared advantages. For GRPO, the z-score advantages have a fixed sum of squares equal to g, the number of completions. But for GOPO, that sum grows with g. Specifically, it's 4g plus 1/3, g1. For small g, say 4 or 5, this is much larger than 1. So even though GOPO's advantages are bounded, their magnitude is higher on average. This inflates the gradient norm, leading to stronger, faster updates. And as we show in the paper, this effect is asymptotically bounded as G grows, so GOPO remains stable even with large batch sizes. This is a rare win. Higher gradient norm, faster convergence, better robustness, all from a simple rank transformation. And it's not just about numbers. Qualitative analysis shows that GOPO generates responses that are more grounded, more coherent, and less prone to hallucination. It avoids unsupported claims. It focuses on narrative depth, identity, and lived experience, especially in creative tasks like writing feature articles. Where GRPO defaults to generic therapeutic benefits like reduces stress or improves mood, GOPO frames pain as a lived experience, agency as a form of resistance, and art as meaning-making. It's not just better at the task, it's better at being human. So where does this leave us? We've shown that reward models are fundamentally ordinal tools. They're trained to answer which is better, not how much better. Yet most policy optimization methods treat them as if they're measuring a continuous, calibrated scale. GOPO fixes this mismatch. By using only rank-based advantages, it aligns the policy update with the signal the reward model was actually trained to provide. It's simpler than GRPO. It's faster, it's more stable, and it's more aligned with the true nature of preference learning. In a world where alignment is increasingly critical, GOPO offers a principled, robust, and efficient path forward. If you're training large language models, especially for non-verifiable tasks, this is a method worth trying. The code is open source, and the results speak for themselves. Because sometimes the most powerful signal isn't the number, it's the order.